All right, so we're going to do number 8. I'll put 8 on the board because whatever I record, I'll post, okay? A given sample of xenon fluoride contains molecules of a single type, and they're xenon F sub n. So we don't know if this is a 1, a 2, a 3, or n is some whole number. Now, if we have 9.03 times 10 to the 20 molecules of xenon, of this xenon Fn, right? And it says that that has a weight, which we know really means a mass of 0.311 grams. Okay, calculate n. So here's the question: if I have that many molecules of xenon fluoride something, how many xenons do I have in that molecule? So based on that, I have 9.03 times 10 to the 20 xenons, and I have some number times 9.03 times 10 to the 20, fluorines. I don't know if this is one of them per thing, or 2 of them per molecule, or 3 of them. I don't know what it is. But if I can get the mass of these xenons, I can figure out the mass of the fluorine that's left in there. The mass of xenon is part of this 0.311. So let's figure out the mass of xenon. We have 9.03 times 10 to the 20. I'm going to need some help. What's the mass of xenon, the molar mass? That's the number. This is the number of atoms. I should write atoms in there.
It's 131.
Okay, so times 131 point what? 30 grams of xenon. Right, for 6.02 times 10 to the 23rd atoms of xenon. That's a 3 there. Okay, so I can figure out how much 9.03 times 10 to the 20 atoms of xenon, how much mass does that have? So go ahead and do that. Okay, so this comes out to be 0.19695, or so we'll say 0.197. So that means that this many molecules has a mass of 0.197 grams. So how much mass must be fluorine in this stuff? Here's the stuff I had. How much mass is left over? So I'm going to subtract that, right?
Yeah.
And we're going to get 0.114.
Yeah.
Okay, so in this pile of stuff, I have this pile of xenon fluoride something. I don't know how many fluorides are attached to each xenon. I know I have 9.02 times 10 to the 23 molecules of xenon F something in here, xenon Fn. I just don't know how many n's are in each one. I know I have 9.02 times 10 to the 23 xenons, which I know is 0.197 grams. So if I subtract that, that means there must be 0.114 grams of fluoride atoms. So if I said to you, you have 0.114 grams of fluoride atoms, and that was the only question, you can do that. So how many atoms of fluorine do you have there? So solve for the atoms of fluorine. 3.612 times 10 to the 21st. That's how many fluorines are in this. Now, I have 9 times 10 to the 20 xenons. I have 3.6 times 10 to the 21 fluorines. Divide those two numbers, and you're going to find that you have a multiple, right? If I do 9 times what equals, so what number do I multiply this by to get my fluorine atoms? Because for every 1 xenon, I have a certain number of fluorine atoms. I'll go to the next page. So we have 3.612 times 10 to the 21. Is that what you said?
Yeah.
Fluorines, right? And if we divide by 9 point, what was the original number?
9.03 times 10 to the 20.
Times 10 to the 20, that was given, and we get 4, right?
Yeah.
So that means that that compound had xenon F4. For every 1 xenon, right, I subtracted all the xenon mass out. I knew how much fluorine mass I had, and when I figured out how many fluorine atoms I had, it was 4 times the number of xenon atoms. Okay, molar density, moles per liter, and we know that the mass density is 1 gram per milliliter, so we have a conversion here that there's 1 milliliter for 10 to the minus 3 liters, gives you 1,000 grams per liter, and then you do this conversion here to get to moles per liter, so the molar density is 55.5 moles per liter, and then if you multiply that out you can get the number of molecules, 1.2 times 10 to the 25. Okay. Good.
That's a lot of work.
One other thing that this problem asked for, in addition to the molar density, was if we had, for 1 mole, if we had 1 mole of water, how many liters would that be? So one way that we want to look at some of these ratios is think about it. If we say 55.5 moles per liter, that means moles per 1 liter. If I flip that upside down, right, 1 liter would equal 55.5 moles of water. Okay, so we're just staying in this one problem here. And if I do that division, that the numeric division here, 1 over 55.5, as a decimal is 0.018 liters per mole. Okay, there's 0.018 liters per mole of water. There's 55.5 moles in 1 liter, and there's 0.018 liters in 1 mole. So you can always take an equivalence ratio and flip it upside down and divide the number and figure out what the reverse thought process would be. And then just, to go back to what we had said, 55 moles per liter, and we can figure out if I had a 12-ounce cup, so we're basically multiplying 12 ounces and converting it, and you get 1.2 times 10 to the 25th molecules of H2O.
So first you have the mass of the crucible with the cobalt-2 chloride, and you subtract that from the heated cobalt-2 chloride, which is the third one because they stay the same, and you get how many grams of H2O were in there. And then you do the same thing, but this time you're doing this by that, and then subtract that from the dry crucible, and you get 1.100 grams cobalt-2 chloride. And then you now have grams, but you have to convert it to moles. So you have 0.916 grams H2O over 1 mole H2O, which is 18.02 grams H2O. And you cross those out because now you're in moles. And you get that it equals 0.0508 moles H2O. And then you do the same thing for cobalt chloride. It's 1 mole cobalt-2 chloride over the molar mass, which is 129.83 grams, which goes away now, and you're in moles, and equals 0.008473 moles cobalt-2 chloride with the significant figures. Then to figure out your multiplying factor, to know how much H2O molecules are in your empirical formula, or chemical formula, you divide each of your moles by the lowest amount, which is, in this case, is 0.08473. So you divide 0.008473 by 0.008473, and you get cobalt-2 chloride 2. And then you have the dot there for H2O. And then you divide 0.0508 moles H2O divided by 0.008473 should be moles moles cobalt-2 chloride, and you get 5.99. Oh yeah, so equals 5.99, which you round to 6, and then you get your answer of cobalt-2 chloride dot 6H2O.
Say hello, my name is Ryan.
So you start with Ca3 and then parentheses PO4 parentheses 2, and then you find the molar mass of this compound, And so you do 3 times 40.8 grams plus 2 times 30.97 grams plus 8 times 16 grams. And you'll get a total of 120.24 grams plus 61.94 grams plus 128 grams. And this equals 310.18 grams, and that's per mole. So that'll be your answer. For number 12, you have to find the percent of hydrogen in all these compounds and see which one has the highest percent of hydrogen. So you want to find the molar mass of all of these compounds. And so you get 36.46, 18.02, 98.09, 34.09, and 20.01. And then you divide the amount of hydrogen by the total molar mass, and you'll get your percent. And then the one with the highest percent equals is the answer. For this problem here, you want to find the molar mass of C3H8NO5. The molar mass of this is 169.09 grams. So then they gave you 688.6 grams. So you want to multiply that by 1 mole over 169.09 grams, which is the molar mass. And this equals 4.072 moles of C3H8NO3P.
So if we do number 2, it says gallium consists of 2 isotopes. So we have gallium, and it says that there's 68.95 AMUs is one isotope, and 70.95 AMUs is the other isotope. And then it says their abundances are 60.16% is this kind, first kind, and 39.84% is the second kind. Now, if it was 50% and 50%, you could just average those numbers. But because it's not equally divided, you have to get what's called the weighted average, which is how you find the average atomic mass. So the average atomic mass is going to be the percent, so 0.6016 times 68.95, plus the percent, 0.3984 times 70.95. So this is 41.5 and 28.25. So when we add those up, we get an average, an atomic average of 69.76.
That should be a 5.
75, okay.
In question 17, the directions ask, well, they tell us that we have a 4.000 gram sample of a substance containing carbon, oxygen, and hydrogen. So it tells us that oxygen is found to have 1.389 grams, and there is 0.526 grams of hydrogen. So I combine these two together and then subtract them from 4.00, and we get the total of 3.137 grams of carbon. So we have all the elements in grams, but we need to convert them to moles. So in each gram, we multiply them by the molar masses. No, we divide them by the molar masses, and then we get these three totals. And out of the three moles, we want to divide each by the smallest mole, the smallest number of moles, which in this case is 0.08681. And when you divide those, you get 0, 6, and 1. So the empirical formula is CH6O.
We have a 1 pound tank of propane, and propane is C3H8. And we want to know in this question how many moles, because if we're going to learn later that if we find the number of moles, we can find out how much heat it'll give off, so we can figure out how much you can cook with it, right? So we need to go from pounds to kilograms to grams to moles. So we'll say, okay, well, 1 pound, like we got to get that into, first of all, into grams or kilograms. And we know that there's 2.2 pounds is equal to 1 kilogram. It is. If you didn't know that, look that one up. But that was from the last unit, right? And then, all right, and then we need to get rid of kilograms because all our molar mass is in grams. So kilo equals what?
1,000 grams.
Right, 10 to the third, so kilograms is 1,000 grams. So I'm gonna put 1 kilogram on the bottom, 1,000 grams on the top, and that's gonna cancel kilograms. So let's get how many grams is a pound. That's just a conversion. We haven't even started the propane problem. Okay, so we have 44.1, no. Okay, so 454.55, so let's just.
We keep going if you want.
Yep. Okay, so I didn't put propane in the original thing, which is why I stopped. All right, so we know we have 454.5 grams of propane. And we know that 1 mole of propane has a molar mass of 36, what would you say, 44.08? 44.11 grams of propane. So we're going to cancel grams of propane, and when you do that out, you should get, okay, so it's 10.3, you're right, moles of propane, but since we started with 1 pound, I need to give you better sig figs to start the problem, so 10.3 is fine. I'm looking to see that you know how to do that. If you had to round that, you would actually just round it to 10.
So would you want to put the point?
No, because there was only 1 sig fig in the 1 pound.
When do you put a
When
point
you need
there,
two.
though?
When
Like
you
if
need
the
two Cs.
1 wasn't there and the 2.2 just was, would you put a point?
If this was 1.0 pounds, that would be 2 sig figs,
And then would you put 10 points?
and then you would put 10 point.
Okay.
I like this problem.
So 13 says we have a sample of, let's see, a substance contains 35 grams of nitrogen and 5.05 grams of hydrogen and 60 grams of oxygen. Is there something else too? 60 grams of oxygen, okay. And then it says, how many grams of hydrogen are there if you have a 129 gram sample of this whole thing? How many grams of hydrogen are in there, right? So yeah, this is a percent composition problem. So you're gonna figure out 5.05 grams of hydrogen is what percent of the whole. So this whole substance, if you added them up, would be what, 100?
It's like 100.05.
100.05 grams. So this little this substance that we have is 105 grams total, and 5 of those grams is hydrogen. So if we do part over whole, we get the percent composition, right? This is of the whole thing, of the whole substance. And so what percent is that exactly? 5 point what?
0.05.
Okay, so 0.0505, great. So 0.0505, which is 5.05%, right? So if I was just ending on a percent composition, I'd say that, so it's because it's so close to 100. But that means that in any substance, if I take a 129 gram sample, well, 5.05% of that sample would be hydrogen. So I would do 5.05% of the 129 is going to be the grams of hydrogen, right? So what is that? 5.05? 0.0505 times 129 comes out to be what?
6.51.
6.51 grams of hydrogen.
I think I'm good after that.
Okay, so number 4 says we have how many? 2.63 times 10 to the?
13.
All right, so 2.63 times 10 to the 13 red blood cells. Okay, and in that, the total amount of iron in all of that is 2.90 grams of iron. And so the question says, how many atoms of iron are in 1 blood cell? So the question is, how many atoms of iron in 1 blood cell? So if we could figure out the number of grams of iron in 1 blood cell, then we can convert from grams to atoms easily. So if I know that I have 2.90 grams of iron in this many cells, this much iron in this cells, what I'm looking for is how many atoms of iron per cell. Well, I know how to get to atoms from grams, so if I can get grams over cells, right, if I could say I have this many grams per cell, well, I know that I can use the molar mass of atom of iron, which they give you, we could say that, well, there's 6.02 times 10 to the 23rd atoms of iron for every 55.85 grams of iron. So the question is, how many grams of iron are there in the cell? Well, there's 2.90 grams in this billions and billions of cells. So how could I use those two numbers to start off my problem here? I want grams per cells.
Wouldn't it be 2.90 over?
Yeah, exactly.
Grams over 2.6.
Exactly. So if I divide 2.9 grams by that number of cells, that will tell me how many grams are in one cell. Anytime you're told a quantity and you have like this much in this many, if you divide them, you get how many in one. But you just have to make sure you get your units right. So if I set this up now, I have, all right, if I divided that, this would give me how many grams per cell. I don't need to stop there, though. I can keep going. So I have grams of iron, cancels grams of iron, and I'm going to get atoms of iron, great, that's what I wanted, per cell, great, that's what I wanted. So it's really a simple problem as soon as you see that this amount of iron is in this many cells. It's like if I said, okay, I have $20 and I have 10 students. Okay, how many dollars per student, right? Well, if you say 10 over 20, that means you each get a half a dollar. If you say 20 over 10, you get $2. It depends on which way you put it. All right, so what do we get?
9 times 10 to the 9th.
1.19 times 10 to the 9th. Okay, atoms per cell. For most people, atoms of iron. I don't carry this much usually because I end up being low iron a lot. So you have to eat a lot of leafy vegetables.